Calvin, Adam, and Roger are here. Excellent. You guys hear me? I cannot hear you. Can you hear me?
How about now?
Yes.
Yeah, I hear Dr. T.
Excellent, excellent. So let's see. Microphone. I think that's the one. Okay. Alrighty. Okay. Let's take a poll. Can you guys see the poll? Yes. Excellent. Oh, I've never polled before. Now I can ask more than yes, no questions, and I can get a quantitative answer, although I cannot tell who's answering. Urgh. Urgh.
The poll is anonymous?
Sorry?
The poll is anonymous?
It's anonymous, yes. Huh. Hey, Kenya, I did not answer your email because I was just too lazy and angry.
Too busy, huh?
Okay.
It's okay. It's okay.
Yeah, I was and yeah, just like, you know, for excitation, there's one up arrow, then there's a bunch of down arrows. I want you to provide the down arrows.
Yeah, so I was a little confused about that because on the assignment there's the red arrows that are going down on each column, and then I wasn't sure if you wanted us to have the arrows all the way to the top, or I don't know.
Exactly.
Or
that's what you got to figure out. So
we can.
Yeah.
What I did, Kenya, is I did all the transition states. So between S or the energy going from ground all the way up to, are you talking about the second one, right?
I'm talking about
part 1 or part 2 of the number 1 question, because there was 2 of them, like the emission or the excitation one.
let me find it.
For example, the first one was the excitation spectra, where the emission was given to us.
Yeah, the emission is the red line, and then the excitation, there's going to be a series of excitation lines, right? Because the excitation, this is the emission spectrometer is set to this wavelength, right? But the excitation is going to scan through a bunch of wavelengths, right? So just do one arrow per, I don't know. I'm trying to do something here. It's not really working. But just like you can put an arrow going up, then another arrow going up. It's like this arrow going up will go wiggle, 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 and then it'll stop here and emit, right? And this arrow going up will go wiggle, wiggle. It'll stop and go down there, right? And then there's going to be nothing in the gap, right? And then there'll be another one like that. So,
hey, Dr. T, would it be the same for all of them then, or is it different?
Pretty much the same for all of them. So the emission spectrum, for example, you put in an excitation energy here, you'll get emission from basically possibly this state down to here, and possibly this state down to here, you know? So this one will go down, 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 and then this one will go down and then down.
So then on the emission spectra, would there be the red line? Is that going to be always like
Yeah.
all the
You can think of it like it's there in all of them. Yeah, I didn't repeat it. Yeah, but it could be there in every case. Yeah.
and
then
then
there'll
just
be
different ways that it can emit.
right. Yeah.
Okay. I thought that the lambda and the number thing like had something to do with it. So I was really confused with that part.
Well, the idea was to then make a spectrum of the stupid molecule using these wave numbers and these lambda values, but I never got to that. So you guys lucked out.
Okay. And then for so are you talking about number 7 then when you're talking about like doing an absorbance or something?
Number 7. Aha, number 7. Okay, so number 7 is here, right? Yes. So you will notice that fluorescence and absorbance are plotted on their side, right? With the fluorescence intensity going this a ways, the frequency going this way, and the absorbance going this way, frequency going this way, then the molecular energy levels starting with E0 are here, right? And they go up in energy, right? And energy can be in wave numbers or whatever, right? So what I want you to do here is I want you to tell me what an absorption spectrum will look like starting from down here close to 0, but not at 0. Because if you put in 0 wavelength, or 0 energy rather, that would be infinite wavelength. So don't go quite to 0, right? But then show me the peaks that would appear for this molecular energy level. And I gave you hints. I gave you big old hints here because these
So is that where the peaks are supposed to be?
Shh, don't say anything. People aren't gonna know to put peaks there. Gotta be quiet. So this is so now excitation, right? You can see peaks pretty much starting up here, right? Because the emission is going to be, the emission you're going to have to follow from this band here, right? So you can, the excitation spectrum can go through all these, right? But the emission spectrum will be different. So they're actually, fluorescence is a misnomer here because there's 2 types. There's excitation and emission. So do both.
Excitation and emission for both absorbance and fluorescence?
No. Excitation and emission for fluorescence and absorbance for absorbance.
Okay.
Yeah. So absorbance is just absorbance, right? There's nothing weird about it. But fluorescence, there's excitation and emission, right? Excitation is where you look at one emission wavelength, which in this case would be starting from this lower level of E1, right? And say coming down to E0, you could look at that wavelength, right? But then you'll scan the excitation over these peakadelies and over these peakadelies, right? And then if you're putting energy in up here, it can come out down here. Putting energy in here, it can come out down here. Putting energy in here, it can come out down here, right? And that is an excitation scan. Now, an emission scan will put energy in here, and then we'll look at all the other levels that can emit, and that will be here and here. But there's a funny little twist there, right? Because the energies on the emission are lower. Because in order to emit, it has to emit from this level here to one of these levels here, or this level here to one of these levels here. Right? So there's a Stokes shift. And I'm going to make you guys, I'm going to make you, force you, torment you into figuring this out on your own. And it's, and if you think I'm going to help you, you're probably right. But I need some good questions.
I have a question then.
Yes.
So, oops. So the emission spectrum is dependent upon the molecule itself, whether it will actually emit from E2, for example, to ground state, right? Or S2.
Yeah,
So,
right, yeah, right. This is, yeah, S0, S1, S2, E0, that's just a name, yeah. So why don't you assume that it will emit, but have it emit from E2 down to the ground state.
Right.
So,
okay. So we assume emission for at least 2 energy states.
Yeah.
Okay.
Okay.
Oh, who's playing that music? Is that you, Dr. Terrell?
No, that was Kai rocking out. Weren't you, Kai?
My bad.
No, you were rocking out, man. You were entertaining the entire group because you had some house music happening there. But okay, so you guys are getting better. I can actually see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 faces. 10 out of, oops, wait, no, there's more people. There we go. I can see Leslie and Kai and Adam and Aditya and Ikun and Ivy and Richard and Carla, Dan and Kenya and Roger and Calvin. And I still can't see Lily or Pauline, but that's okay. I'm not trying to pressure anybody. I'm just sort of embarrassing you guys unintentionally. So forgive me. I do like to see faces. It makes a huge difference. So
I have a webcam on my iPad, but you're mostly going to be looking at the ceiling if I turn it on.
okay, I got it. You got an iPad, huh? I almost bought one of those guys because I was sort of freaking out over summer. Like, what am I going to do? How am I going to teach online? I don't know how to do this. But
I use it for notes.
Yeah, I know that's really pretty cool. That's why I wanted to get one. And I was thinking, oh, I should buy a Samsung tablet-y thing with a pen, you know. But then I looked at them and they're like, oh, those things are $500, man. And then the iPads are like $900, yeah.
Nah, this one was, I think, 200. I don't have the expensive one. I do not have the expensive one.
Really? And do you have a stylus you can write with?
Yeah.
No kidding. Wow. You got to show me that. Are you sure you're getting it from Apple from America, or is it Apple spelled with 2 backwards P's and they come from
Russia? It works, and I've had it for a couple years, so whatever it is.
That's amazing. That's amazing. I love it. All right. So, you guys can see this this thing, right? So do you think you guys are going to be able to get through it?
No.
No.
I'm gonna try my best, Dr. T.
Okay. Well, I got one try my best and one no.
I'll get back to you on that.
Okay. So it's not hard. It may be a little bit opaque, right? But it's not hard. Let's do absorbance. Let's do it together. Can we do absorbance together?
Yay.
Okay. So we're going to start it at, you see these lines here? Can you guys see what I'm indicating on the screen here? Yes, Richard, can you see? Yeah, good, excellent. So in that case, for each of these lines, there'll be like a little peak, right? And, you can add a little bit of broadening to make life interesting for me, and maybe make some of the peaks higher than the others. That's really cool.
Does it matter
really-
how tall they are or how short they are? Because aren't we basing that off the energy thing?
Yeah. So the joke here is that we can't. I have no information about how intense, how tall, i.e., intense to make them. So basically, we could just indicate with a line where the center of the band is going to be, right? But you can also draw the peaks a little overlapping or something. It doesn't really matter, right? So you'll just draw blink, blink, blink here. Then you go back down to baseline because in this energy range, there are no states. Then you're going to go blink, 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 and then no states, and then blink, 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 right? Just draw the freaking absorbance spectrum on there, right? Now, what I was trying to do above was get you to appreciate that these are all sub 10,000. So this is like 3,000, 2,000, 1,000 wave numbers, right? So let's say that this is 3, 2, 1. So this is 3,000 wave numbers here, right? In energy. Now, who can tell me what molecular energy sink there is at 3,000 wave numbers? Dan.
At 3,000 wave numbers,
Yes.
vibrational energy.
Yes, it's vibrational. Very good. What is vibrating? Aditya. I don't know is a valid answer. If you don't know, it's basically you know or you don't know it.
I don't know.
Okay. Who knows what vibrates at 3,000 wave numbers? That is a hydrogen atom bonded to a carbon atom. Bing. So CH resonances will be at 1, 2, 3. So this is going to be 1,000, 2,000, 3,000. So there's going to be like right in the middle here, there's going to be, well, if there was a level, it would be carbonyls, right? But that's just like an example of what these might be, You got low frequencies like bends, you've got intermediate frequencies like heteroatoms, then you've got CHs up here at 3,000, right? I don't know. I'm just making this shit up, right? But the idea is that the energy level diagram for absorbance corresponds exactly to the energy level diagram of the molecule. Because if you start at D0 and go up, and you start at 0 wave numbers and you scan up, then you will see these peaks here. I see cognition happening. That's good. That's good. Nobody does this. Nobody, but this is true. This is true, right? Now, when you get up here, you're going to be talking about red light, right? So this is This is like 10,000 wave numbers. Let's see. 10,000 wave numbers here. So this is 1,000 nanometers. Right? And this is 250 nanometers here, 40,000 wave numbers, right? So this is 10,000 wave numbers, or 1,000 nanometers. And this is probably so then we get up here to about 40,000 wave numbers, I think. 40,000 is 200 or 250. Not sure exactly how that works out.
So, Dr. Terrell,
Yes.
to clarify, we're sketching spectra and not energy level diagrams, right, for this problem?
Right. On this part of this problem, we're doing the absorbance spectrum. So it'll have a bunch of lines here, a bunch of lines here, then a bunch of lines here, right? And that's all it's going to have. Right? And, if there were such an instrument, that if there were a single instrument that could measure across all these different wavelengths, then we could plot it on the same spectrum. And it used to be that you could take an FTIR, and then a near IR, and then a UV vis, right? And you could knit together the entire frequency spectrum from, say 500 wave numbers up to 50,000 wave numbers, right? And that would give you an idea of the whole molecule, right? I mean, it's not really super informative. That's probably why it kind of went out of favor. But also, there's just a type of instrument that operates in these energy ranges and another type that operates in this energy range. This is the Fourier transform instrument, and these are the UV vis. So this is vis, this is UV. Okay, so now for this guy, fluorescence, we're going to have two types. We're going to have excitation and emission. Right? So excitation is going to look at a wavelength that corresponds to, let's say, this transition down to here, right? So there's going to be a downward arrow here, right? Now what we're going to do is we're going to look at the excitation spectrum starting just to the just to the blue of that, and it's going to go up here, here, and here, and that will produce peaks. And here, 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 and here, that will produce peaks. So what you're going to do is you're going to put peaks on these frequencies, right? For excitation.
Is that going to be 4 peaks or 3 peaks?
Okay, so in this guy, there'll be 3 on the bottom because you can't actually, normally you don't look at resonance.
Won't the vibration peaks kind of blend into the main energy?
Yes, yes.
So shouldn't there
yes.
only be 2 from the E1 to ground and E2 to ground?
Okay, so
not 3?
It's either way is actually fine, right? Because it depends on how much broadening the environment creates.
Right.
So if it's a low broadening, let's say you have molecules in the gas phase and you're doing fluorescence of gas phase molecules. In that case, you'll see these spikes, right? If it's in a low dielectric solvent, you'll see resolved peaks. And if it's in a high dielectric solvent, you'll just see one broad peak for this collection of vibrational sub-energies. Does that make sense?
So then, Dr. T, when we're doing the peaks on the graph, should we have two different colors of peaks to distinguish from emission or excitation? And
You can, sure, that would work. You can offset them. You can different color them. You can make one dash and one solid. You could do one in special fluorescent ink. That would be cool. Or you could do one with, there's a rainbow ink, and that changes color every time you move it. I like those.
yeah, it's really hard to do it with my mouse.
Yeah, I know.
I should have an iPad, but
I know. Okay, so now the excitation, right, is going to produce a peak every time light comes out at this wavelength, right? So when you get to an energy level, then energy is going to go in, funnel down, and be emitted, right? You get to this peak, it'll go in, funnel down, and be emitted. Get to this peak, it'll go in, funnel down, and be emitted, right? So the excitation spectrum will look qualitatively very much like the absorption spectrum. You can't do it in the infrared, right? But if you look at the visible and the ultraviolet, you will see an excitation spectrum that looks almost exactly like the absorption spectrum, right? Because in absorption, you're looking at energy that's being snapped up by the molecules. And in the excitation, you're looking at energy that's being snapped up by the molecules and converted to fluorescence at the longest wavelength that you can measure. The longest wavelength meaning the lowest energy. Right? And when you do excitation, you plot versus the excitation energy, or the excitation wavelength. How are you doing, Hikun? Excellent. Ivy.
I feel a little obtuse. Like,
okay. I like it.
I understand the explanation, I guess, but I'm having trouble visualizing how to physically do it on the plots provided.
Yeah,
okay.
I agree. So are we doing one peak like in the space between the two lines, or is one line a peak?
No, you're gonna, yeah. So hold on. I knew I was gonna end up doing this. So hold on just 1 second. You see, all you got to do is ask me stupid questions and I will answer them. But you have to ask. I'm going to go back to screen 1 here. I'm going to bring this guy down. And actually, why don't I go ahead and get that stupid thing?
It's the second to last one on the list.
There we go. There we go. Excellent. Thank you. So here we go. Oh, wait, it's down here, right? There we go. So now I'm going to sort of manipulate things here a little bit. There we go. All right, now can you guys see the thing that we're looking at? Good. It's always good to see what you're looking at. I like that. So let's just say that we're going to talk about the excitation spectrum. Right? No, you have to let me draw. We're not going to do this. Up, 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 up. I'm not going to mess with you. Are you going to? Good. Okay. So let's see here. And I found out how to get more colors. Just right click, modify the tool, and you get all these different colors. So let's pick a nice red. Orange, red. Okay. A nice red pen. The red pen is going to identify the emission wavelength. This guy here, I'm going to label it lambda EM. Right? And it's red. Why did I make it red color?
To bamboozle all the colorblind people.
Oh, are you colorblind, Kenya? I don't believe
Kevin's not here right now, though.
you're not colorblind. Who? You're not. You're not. Who is colorblind? Tony was colorblind, and Kevin Law was colorblind. But who else is? There's no colorblind people, are there? Okay, so I am not ADA approved.
Is it because it is relatively low energy, therefore longer wavelength?
Yes.
So in the
exactly. Exactly right. Lambda EM, it's going to be about 1,000 nanometers. So it's actually near infrared, right? Or 10,000 wave numbers. Right? So now the excitation spectrum is going to start. I need a new color. Let's make it green here. So now the excitation spectrum is going to start here, right? It's going to end here. And it will be 0 on the fluorescence intensity here and here, right? And the reason that I started here is because we have to start it not at the exact same wavelength that we're collecting the emission. Because if we put in light at the same wavelength that we're looking at the emission from, normally what we see is a lot of Rayleigh scatter. And so we can't tell what light we're seeing is due to Rayleigh scatter and what light is due to resonance fluorescence, if there's even a difference, right? So actually, let me start this guy here, right? And let's just say that we see something like that. Now, I gave you guys too much information there. You didn't see that.
This is a recorded lecture.
Oh, oops. Okay. Now you have to watch it. Fast forward, fast forward. You're gonna write a script that looks for the color green. So basically, yeah, it'll go. So you'll start it if you start at a long wavelength and go to a short wavelength. Like a lot of times, actually, they start at short wavelengths and go to long. So in that case, it will look like. That's all. That's all I'm looking for. I just want you to connect the energy levels with the spectrum, you know?
So I'm confused. Did you want peaks or arrows?
I'm sorry, Pauline. All I got was Dr. T. Wing, 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 wing.
She's having issues with her Wi-Fi. Do you want the mountains or the arrows?
Ah, well, you could put both in and I would not be disappointed. But I definitely want the mountains. And what do we call those mountains? Fluorescence, what?
Peaks.
Fluorescence, you've got, there's really only two choices. It's fluorescence, blah, 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 or fluorescence, blah, blah, blah.
Emission?
Emission is wrong. It is excitation. Oh my God. Okay. So now we know. So now for emission, the emission spectrum, right? What we're going to do, you get a pen here, and I'm going to get the violetest looking pen I can. Dark blue, I don't know. Blue. No. I'll use indigo here, right? And now what we're going to do is we're going to go in with indigo here. Okay? And we're going to excite up to this level here. And this guy here is going to be lambda EX. Then we're going to look at lambda EM. That's an interesting new frequencies, right? So here's where it gets kind of interesting, right? Now, what happens to this molecule after it goes to this level here? If you EX it up to here, what's the first, it's called a photophysical process. What's the first damn thing that happens to that molecule when it's excited up to this E2V4 level? E2V3.
Little wiggly thingy.
Yes, you got a squiggly wiggly down to there, which is what kind of decay?
Non-radiative.
Non-radiative decay. Excellent. NR, non-radiative decay. Excellent. Now, what happens next on the way down to the
It's a straight line down.
straight line down? And where do we stop?
Anywhere?
Okay, good. We can stop here. We can stop here. We can stop here. Or we can stop here. Right? But if we stop here, we wiggle down to here, right? So now this is the total energy loss here is these wiggles plus this straight plus these wiggles. Right? Now that energy produces an emission at a wavelength corresponding to, or at a frequency corresponding to the difference between these two guys here. Right? So that guy here is going to be, if we take these guys and we move them down here, they're going to be from here to roughly here, right? And that means that the first peak in the emission scan will be here, right? And then it'll be lower energy. Right? This kind of thing will be repeated here, right? but there's a, this is called a Stokes shift. Right? And then there will be arrows that come down here and skip this whole manifold entirely. They go there, 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 and there. Now we've got this guy here, right? And translating that guy here, pull it down here, and then go up, that is going to be a similar shift up there. Does that make sense?
I don't really understand how
I
you
think
decide.
Yeah, go ahead.
This is Carla, not Ivy.
Hey, Carla.
I don't really understand how you're deciding where to place these peaks.
I know, and I'm not going to explain, but Ivy's going to explain.
Explain which.
Explain to Carla why these peaks go here and not here. I'm going to sort of decongest this whole mess. Right? So, or why these peaks are here and not here, right?
To my understanding, isn't it due to because the vibrational relaxation is not radiative, therefore you're losing energy. We'll assume that's where you're only losing energy. So you basically shift it down by the vibrational amount. So whatever that distance is between the upper vibrational state and the lower vibrational state, you're basically shifting it to a longer wavelength.
That is absolutely true. Yes, it's absolutely true. So the part of the trouble here is that we're no longer anchored to this point, right? When we did excitation, we were anchored to this point. But when we do emission, we're sort of more like anchored to this point. We're just, we're looking at the emissions that come out of the molecule. When you excite it up here and then it wiggles down, and then it comes out, and then there's this amount of radiation, this energy of radiation, right? So this first energy, this is the lowest energy. This will come out here. This comes out down there. Does that make sense?
Wait, why is that the lowest energy?
Because the arrow is the shortest.
Oh, okay. So then the shift is just because you have to move it a little bit more, I don't know, because of the Stokes shift thing that you said?
Right, right. So if we were to take this arrow here,
Okay.
and move it down here, it would be right there. Right? So maybe I could color code that instead of crayoning it to death. Okay. I'm gonna try again. Get something sort of sort of maybe, possibly. Okay. I'll use okay. I'll use black for the non-radiative decay, right? So we got non-radiative decay down to that level, right? So this is the excitation. The green is the excitation. Let me draw that in. Green. This is the excitation. purple, and now, so we've got red is the emission wavelength for the excitation scan. And now let's do blue, draw. Blue, 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 blue. Blue will be the emission scan, right? And the emission scan will have two parts. Right? It'll have a part corresponding to this one, this one, this one, and this one. Starting at the base of an electronic level and moving into the vibrational levels, right? Then it will have another branch that's goes down further and goes to here, 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 right?
So really quick, it goes from energy level 2 to energy level 1, and it'll fluoresce from that transition?
Yes. Yeah. Let's, yeah, because I mean, it's not always true, but it's possible. It's definitely possible for it to be able to emit light going from 2 to 1.
Okay.
Right? And now it's also possible for it to emit light going from 2 to 0. But it always does so from E0 of E2, right? Partly because that's how we set it up, right? Because our lambda EX goes into E2, right? Then there's a fast non-radiative decay through the vibrational levels. And then there is a radiative decay down to this level, this level, this level, to this level, right? So there's like nothing happening going down there, then there's something happening, then nothing happening, then something happening, right? Now the tricky part here is that these arrows, which are now this long, this long, and this long, and this long, they translate into an emission scan that's, let's just say, can't start at 0. Let's say it starts here. And it goes 2, 3, 4, right? It's going to have its mountains here, starting at a distance from 0 equal to, actually that's not accurate enough. Let me get that right. It's going to have approximately it's going to start at this energy here, which is equal to this energy here, which is equal to that energy there. Then as it goes up, it's going to have another set of peaks, 1, 2, 3, 4, right there. And these will be, these and these correspond, but there's a shift in energy. And that shift is the Stokes shift. It's just the relaxation energy of the excited state.
Dr. Carroll.
Yes.
should there be a third set of peaks because of the E2 to ground state?
Hold on just a sec. There is, make this thing cooperative. That's not. Okay, there I am. Okay, so is there a third set of peaks, right, corresponding to radiative transitions from these states going down? Is that sort of what your question is?
Well, just from E2 to
from ground. E2, from E2 to ground. Yes. So from E2 to E1 are these guys. They're from E2 to ground. Ground being within this manifold here is this set of peaks. Right? Because you pump in energy here, it decays down, and then it goes boom, and we get fluorescence. We get, we could say, I could draw another arrow alongside here, right? We get a photon for this transition, fluorescent photon out. We get another photon this transition, get another photon this transition, another photon that transition. And those 4 photons are these 4 peaks. Right? Yeah, you just have here, it's just about the length of the arrows dictates the energy of the photon. Does that make sense?
So would there be overlapping peaks for the first group there? The E1 and then the E1 to ground state are like roughly equivalent lengths.
You're talking about in the emission scan. This is the emission scan. In that scan or the excitation scan?
The emission scan.
Okay. So the only peaks you see in the emission scan are here, which correspond to arrows coming all the way down, and here, which come from arrows actually from these intermediate states here, these intermediate states here.
Dr. Terrell?
Yes.
I just wanted you to know that sometimes when you're pointing things, we don't actually see a cursor. So confusing.
Okay, I'm very sorry.
You draw something around it, yeah.
Okay, let me see now. Oh yeah, it's like microscopic. Okay, I think I can do something else. I'm gonna hit the escape key. And I can, oops, touch. And there's this thing called a, oh no, that one's only on PowerPoint. It actually lets you use it as a pointer type thing. So I should go back to insert. Like, can you guys see this arrow?
Yes.
Okay. All right. So I'm sorry about my invisible pointer there. Invisible pointers everywhere. think so. These peaks here are from these transitions, and these peaks here are from which transitions, Richard? Oh, I know. I got your question now. Overlapping, because we have also these transitions, right?
Yeah.
Right, we've got these and these. And yeah, that's completely possible. Completely possible. Yes. Yes. I just sort of overlooked that. So let's just assume they're identical and make them completely overlapping. And, you know, if you want to really super highly impress me, you can do like little doublets there or something. But yeah. Okay. Who else got that? Yes, Carla.
Can you repeat which peaks correspond to which? I was still having a hard time seeing what you were circling.
Exactly. Okay, so I think I'm going to go back to draw. Go back to eraser. Right? Now I'm going to erase the crap out of this thing. Draw. Okay, I'll go back to this guy. I'm going to try to erase here. Here, good, excellent. Okay, so now oops. So, for the emission spectrum, the there is a fixed excitation wavelength, right? A fixed excitation energy. And that excitation energy is indicated in purple. It's indicated in purple. Oops. Hey, give me my, go away. Oh, come now. Go away. Sketch the absorption. Sorry, this is awkward. I'll get there. So, I think it was the draw with touch thing. So, can you see that little wiggly thingy circling around there?
No.
It's what I'm trying to indicate the state. Here, let me actually erase this lambda EX here. All right. So so lambda EX, the excitation wavelength for the emission scan, leaves us in this state right there. Does that make sense, Carla? Leaves us in the top state, right? And the next thing that happens physically is that the molecule sheds vibrational energy, right? And then, let's say that it comes down from here and lands there. Did you guys catch that? So we excite into this level, it into the top level, it vibrationally deactivates to let's call it V0 E2. And then it emits a photon going from V0, E2 down to E0, V3, right? Now, the length of this arrow determines the position of the peak in this spectrum. And I'm saying that length corresponds to something like that energy right there.
And when you say that point right there, do you mean that one peak or the set of all four?
Okay, good question. So the next peak up comes from the next peak down, and the next peak up comes from the next one down, and the last one up comes from the last one down. Leslie, how are you doing?
Good.
Yeah?
Yeah.
Everything makes sense, more or less, so far?
Now it does, yeah. But when I was doing the homework on my, it was not making sense.
Got it. Okay. Well, I'm glad we came back to it, right? This is something I've been trying to sort of teach in many ways up to now, and so I'm glad that you guys can be my guinea pigs here. All right. So Kai, how are you doing?
I actually understand it a little bit better now compared to when I was just looking at the problem, and yeah.
Good. Excellent. All right. So now remember that you can do absorption, right? Absorption is easy. There's just a peak for every line, right? Excitation is easy because there's a peak for every line, but we don't overlap the beginning of the emission and the beginning of the excitation, right? So absorption and excitation are both easy, right? It's just this emission one that's a little bit weird.
Wait, Dr. Terrell?
Yes.
So, since there's a line all the way down to E0, like the little fourth one over here, why, and from what I was following, each little line, like little arrow that's in the vibrational state, that's a peak on the one that's above it, right? So if it's a straight line, why is there peaks on the near the E2?
Are you talking about?
Yeah, those peaks. And then the emission is going all the way to E0 with no little arrows in E1.
Oh, right. Because it can.
Oh.
Because it can.
It can just
go right past.
And it would still have peaks on there?
Right. It would have a peak for every point that it stopped at.
But you just said it went through.
Sorry?
But you just said that it can just go through.
Oh, yeah, right. It can go through, it can also stop, right? And in which case we'll see peaks corresponding to these guys, right? Let me I'm going to clean this up.
Just as a generalization, most molecules don't actually go from S or E2 to E1 though in fluoresce, right? That's mostly a non.
I'm not sure.
Oh.
I'm not really sure. I'll try to figure it out, but I may not have an answer for you. But I'll try.
I thought I remembered seeing it in the reading. That's the only reason why I asked. But
Well, then you're probably right. I read that thing, but then my lack of attention span got the better of me. So I'll look at it again, and then if you can find it, then point it out to me, and then you get a tuition refund.
That would be nice.
Yeah, wouldn't that be cool? So this long arrow here. Sorry, this. Oh no. This long arrow here corresponds to these peaks up here. And then a shorter arrow down here corresponds to these peaks right here. Does that make sense?
Yeah.
Okay, cool. So we're getting into the bovine analogy territory here, or the equine analogy.
Wait, can I ask a question real quick before?
Yeah, absolutely.
So on the energy diagram on the side, like at the very
over here, right?
Yeah. Are we supposed to do anything on there, or are we supposed to just use that?
No. That's just for your reference. Just for your reference.
All right. Thank you.
Good. All right. So we are in the equine analogy territory. Do you know what that means? That we're beating a dead horse. So we're beating a horse, which is not responding very well anymore. So I think we should move forward. Do I have your permission to move forward, or shall we stay and beat the horse for a little while longer? All right, I got a thumbs up from Ivy. That's awesome. So that means that we're going to move forward. Hold on, I got to talk to my wife. Hi, honey. How are you doing?
I'm good, honey. Are you done teaching?
No, I'm not. I'm not done yet, honey. I'm still teaching.
Okay, call me after you're done now.
Okay, baby. Get her to show up. She's going to show up. Okay. So, what are H and J aggregation in fluorophores? You guys can look that up, man. They're different types of aggregates. What effect does it have on fluorescence, both in the wavelength area and the efficiency area, right? So let's do a quick poll here. Let's see. Let's do a poll. Okay. Okay, that's not the right one. Polling is closed. Edit. Okay. Oh no. Forget it. I'm not gonna try. Too stupid. Okay. So oh, now where am I? I don't even know where I am anymore. Okay. So what is the energy coupling formula for dipole-dipole interactions? So if you actually define the terms in that, I give you brownie points, bonus points, right? It's going to be J equals mu times cos theta, right? 1 minus 3 cos theta squared, that type of thing.
Wait, you want the equation on that, not just like J has low Stokes shift, or wait? Oh no, you want Coulomb's law? Or
No, there's a formula. It's
oh,
in the Smiles paper. It's in the Smiles paper. I'll even tell you what paper it's in. Okay. Now, an exciton is mentioned in the Smiles paper next, and I want you guys to define it. Now, there's a variety of ways to go about this, and there's not a real wrong way and a right way. The easiest way is to type exciton into Google, and it will bring you to a Wikipedia page for excitons, and it'll give you this sort of weird, sort of scholarly sounding, very general explanation of an exciton. You know? But what I was actually kind of hoping for was to involve the ideas of energy transfer, like Forster transfer of energy between dye molecules situated, close to one another. Right. So if you have as opposed to an isolated fluorophore, you have an array of fluorophores, and one of them absorbs a photon and becomes excited, it can actually transfer that excited state energy to molecules nearby. And it's, I don't understand that. That's kind of strange to me, but it happens, right? And when it does that, the nerd in all of us kicks in, and we have to give it the name of a quantum particle, an exciton, because it's excitation energy, and now it's a ton because it's like an excitation that travels around the crystal. Woo! Right? So it's an exciton. But it's just the energy just moves from molecule to molecule. Now, granted, it's pretty cool because it's completely elastic. It moves from one to the next. But it's also a hopping mechanism, right? It's not like an electron that flows. It hops from one site to the next. And then when that excited state energy gets to a molecule that's near a defect site or has some way to dump the energy non-radiatively, it goes dark. It dumps it and goes dark. That's why excitonic stuff, it makes the lifetime longer because it has, goes from molecule to molecule and it gets its lifetime over and over. And then when it hits a defect, normally then it dumps its energy. And only occasionally does it relax radiatively. Does that make sense? Yes, it has to make sense. Who can paraphrase what I just said?
Could I try?
Yes, please.
Okay, so when an exciton is when you have an array or a crystal of dye molecules, and when you excite them, the excited state energy can move around the crystal to molecules nearby until it gets near a molecule, which is near a defect site where the energy can be dumped, and the energy disappears and it no longer emits light.
Amazing.
Okay.
Yes, exactly. 10 times clearer than I said it. You have to be the new teacher. Yes, please, please. It's so much work, please. Okay, all right, I'll keep teaching. But you keep listening. That's awesome. It's so cool. It is so cool. Okay, that's the last question. Okay, all right. Okay, so, all right. So I think that we are officially done with fluorescence. We're just going to slam this chapter shut because I'm sick of it. I'm sick of it. I don't want to think about it anymore. I'm done.
Another quick question?
Yeah.
For number 7, the one that we just went over, is it okay if I take a picture of the drawing I made? Because I don't know how to make the peaks and stuff for the side.
Absolutely, no problem. Yeah. Yeah, if you can hand sketch it, take a picture, it'll still be fine. Scan it, picture it. draw with a mouse, whatever you want. We're all good. Hey, Robert. Would you like your drink? I would love my drink. Ah, he's going to make me a gin and tonic. T minus 4 minutes and counting. All right, you guys have 4 minutes left to ask me questions. And then we're going to do Raman. Okay, we're going to do, this is from my 155 notes. So you know it'll be relatively non-screwed up. Right? We're going to do vibrational spectroscopy, infrared Raman, and then SIRS, we're going to do a surface enhanced Raman. And I'll put these notes on the web. Okie doke. Are we done? I promise you this is, oh wait, spectroscopy. It's probably not spectroscopy. Oops. There we go. Spectroscopy. There we go. Okay. You guys are good at giving me the silent treatment. Lily, how are we doing?
We're good. We're better than we were at the beginning of class.
Okay, good, good. And when is this stupid thing due? Is it due tonight?
Yeah.
Or tomorrow? Okay, great.
Yes.
So you got a little bit of work to do then. Cool. And I gave away all the answers. Pretty much. Okay. All right. So I look forward to chatting with you all next Tuesday then.
Wait, Dr.
Okay. Yes.
Are you posting this lecture tonight?
Yes. Yes. I will post it as soon as I can. It takes me approximately 1 hour though, because it's got to get over to YouTube and then back into Canvas, but I will. I will post it tonight. Thank you, Robert. Check this out. $7:14.
You're still recording, Dr. Darrell.
I know, but it's lecture's almost over. 7:14.
It's 7:15 somewhere, right?
That's right. Let's see here. 7:14 and 48 seconds. 50. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cheers. Not bad. Not bad. So yes, I will post it ASAP.
Thanks, Dr. C.
Alrighty, guys.
Thank you. Thank you.
Do your best. Do your best.
Thank you.
If everybody flunks, I don't know, I'll do something. Don't worry. Everybody's going to pass. No worries. I'm too old to fail people now. Or end.